Okay, so this is a section on the inorganic and the metal complex. This time I'm going to do the lecture number 2, part B, and this time I'm going to focus on isomers and the d orbital splitting. So this is a ligand, and I will just emphasize once more when you're looking at this nomenclature, particularly the En, that means an ethylene diamine, and OX means from the oxalate ions, and ligand has essentially those the lone pair electrons, and the number of lone pair electrons for this ligand is more than one. So this one is, you see the lone pairs. Even this one, you got 4 clinging the site that they can give out the lone pair to the metal complex, to the metal sitting in the center. So the number of lone pair is a 2. This is a didentate, and this is a 4-dentate. Okay, so they are very effective in the sharing the lone pair electrons to form the metal complexes. Nomenclature that what you find out, it has a different names. For example, cyanide, hydroxide, chloride, bromide, they all has anions, and all the anions has ended up with an O, hydroxyl, cyano. Okay, and when you have a neutral molecule such as water, they have a lone pairs. Carbon monoxide, actually they have a lone pair too, if you look at the Lewis structures. And these are the one has his own name, aqua, imini, carbonyl, for those molecules. And an EDTA is an interesting one. If you look at an EDTA, they are -4. You see this? There's a -4 charges from the 4 carbonate, and they should ended up having acetato, and which should be actually under these categories. I don't know why this one is shown up here and here. And I have written and show you how you can name those compounds by understanding the charge state, and then naming those two, and then putting in an alphabetical order. This time I'm going to just skip this one. The second one is also what is called the isomers, and this is actually coming from your lecture slide that you have found out in your lecture note. And I am going to just show it to you one more time on to this. And I'm here just wanted to emphasize you what do you mean by cis and what do you mean by trans. And this time I'm just going to a little shortcut way because I want to focus on the rest of the problem. So you can think about this is a cobalt with a N, diamine, with a dichloro, right? And the ene means a diamine. They have 2 arms, 2 docking site, 2 lone pairs from the 2 amine group, and there are 2 of them, right? So the effective number of coordination is 4 from the En. And then what about the chlorine? Chlorine is just 1, there are 2. So overall, this is a 6. 6 coordination means an octahedral. Okay, so 6 octahedral coordination is what you have, and the octahedral structure is, trying to think about, you can put a piece of paper in a square lattice, square plane, and then you put one on the top, and axial you put on the bottom. So those are the one, if you think about, imagine yourself, there is almost like a pyramid. You can think about the pyramid, having a pyramid just looks like that, with a square plane in the bottom, and there's another pyramid upside down, right? And this one is almost looks like, therefore, octahedral means 8, hedral means faces. Okay? So that's why it's called the octahedral. So the octahedral can have an axial and the bottom position. And then when you have something like chlorine, which is, we can keep track of the chlorine here, and when you have a chlorine here, and if the chlorine is a neighboring, it can be here, and I can use a little thingy that I find out. So you can put it here, you can put it there, you can put all these 4 places. They are the one essentially perpendicular each other, which we call the neighboring chlorine. But if you put the chlorine the other side, there will be the opposite side. So this is only what is called a trans. So I will just the chlorine put on this side, and this time I'm going to this one as a cis compound. And whereas if you're having the chlorine, and this time let me just use the same colors, putting something like this. And if you have this one, and it has to be on the opposite side, and that's what we call trans. Okay. And I also share this. I look at the lecture slide, and this is actually trying to teach you that when you look at this section here, and say when you have a cis diene dichlorometal complex, and they will have these mirror images for this compound, and you hack the mirror images, and then when you put this one, bring it to here and then rotate it, this actual position move to the back, whereas this one is this actual position of amine moves to the front. So they are what is called, they are not superimposable. Not superimposable. So what that means is this molecule and this molecule, they are different. Okay, they are different. So that's why we call the isomers. And this one is, in a very naive sense, not many people say that, they are like a mirror, M-I-R-R-O-R, okay? They are mirror image isomers, okay? Mirror image isomer. And other name is optical isomer. Other name is chiral isomer. Isomer. Some other student actually said the enantiomer. And this is all the same thing. It's just a very important discipline of the chemistry, the understanding the three-dimensional structure. The people has developed different names. Enantiomer. They are the same meaning of the saying, the essentially same one. And even I would even dare to say, nobody's saying this way, but how about left versus right-handed isomer? If you think about left hand and the right hand, they are different. They are mirror images together, just like here. These are the mirror images from both sides, and you cannot put your left hand to the left hand gloves to the right hand to the left hand glove. So they are different, and this is more optical isomers. Just to think about that, and that will help you to understand this concept better. So right-handed isomers. And that could be another concept. But most common way that people saying what isomer is, they call it optical isomer or chiral isomer. When you go to the in your second year organic chemistry, they probably use the word enantiomer a lot more. Those are the more like a made up name by me, and then but it can give some other ideas what that means as well. So having said that, this is one of the take-home messages that can come out from this number 2 in this page. What I mean is a cis. If you have a cis metal complex with a diamine, with a, let's say, dichlorometal complex, they can have an optical isomer pair. They can have optical isomers, okay? But if you have a trans metal En2Cl2 optical isomer, as you can imagine, they are actually symmetric. So optical isomers is not possible for the trans. Okay, so this one optical isomer is not possible. I can even scratch that out. But those who can have an optical isomers is only for the cis portion of this compound. And there's one more. This is a slide. I will blow it up for you guys to see it. This one is, you can see that metal have a 3 ion, and they superimpose. They kind of put the mirror plane projection on the other side and trying to rotate it, they find that it's also not superimposable, and you can do it for your practice. What that means is if you have a metal with a En to the 3, that's an octahedral complex, and this one also can have it can have optical isomers. Okay, so to remember these two, they can have an optical isomer. Cis can have an optical isomer as well. Okay. We have some more people joining in. Thank you very much for attending this. So I will continue to solving the part B, focusing more on the isomer part. And so this is a part that now I'm continue to going into what I call the geometric isomers. So these are all, in big sense, geometric isomers. And depending on whether you have a 2 ligand or 3 ligand situation, geometric isomers, they are different kind. And 2 identical isomers attached to it, we call the cis and trans. And you have 3 identical isomers, and it has a different unique name. This is unique for the not common in actual organic chemistry, but it's common in the knowledges in inorganic chemistry. They call the FAC versus MER isomerism. Okay, that's only for when you have 3 identical. In other words, if you have the B3 ligand, when you have 2 isomers, and if you have 2 ligand, like just as a B2 as a ligand forming the metal complexes. So as far as the 2 metal geometric it's a B2 cases, 2 metal complexes. They are cis trans isomerism. This is coming from your class slide. I just wanted to recap this. And when you have this is a case when you have square planar complexes. So you form the square planar complexes. And in this case, let's say put the platinum in the center. And then you're going to put the chlorine on the same side. Okay, let's do that first. And then you can put the chlorine on opposite side. So let me put it chlorine on the opposite side. And this is what we call the cis, and this is called the trans. And that's opposite side means trans. I like the trans because it's much easier to understand. Cis is essentially on the same side, adjacent to each other in the neighboring side, and like this. This one looks like there are 4 coordination, and this is an NH3 here. Sitting in, and looks like a 4 coordination of the ligand that you see, but actually what's happening if you refresh your memory before, this one actually have 2 lobes of lone pair electrons. Okay, and so electron domain geometry is actually still octahedral. It's just the molecular geometry is a square planar. So that's a thing that if you can remember. But the point up here is whether you want to see the 2 attachments, cis and trans geometry, whether it's an opposite side or the same side, we can happily call this. We can subdivide it, and this one and this one obviously have a different polarity. And so this is, I guess, is polar, so they have a different boiling point and different physical properties and so on. So geometric point has a different physical properties. So when it comes down to the molecular, so this is mainly about the molecular structure of M2B2, and that's a square planar. It has to be a square planar. But when it comes down to the M4B2, okay, we can focus on this B2, whether in the similar side or on the opposite side. And so we can first see, okay, so I can see that this one should have an octahedral geometry. So this one I'm going to place a square. I'm going to put it upside and put a pole there within the square. So this is what I can draw. And then I can put the metal in the middle. Okay, so here is for example cobalt in the middle, and the chlorine, right? Cobalt in the middle, and the chlorine on both sides. So I can put the chlorine as long as let me start with something easy. So chlorine, this P, chlorine, if I can put the chlorine on the opposite side, that will be the trans, okay? and anywhere is going to be cis. If I put this one, it will be adjacent side. If I put it there, there will be a 90 degrees. Even this one is a 90 degrees. That's a 90 degrees. So the only trans is here, okay? And then, whereas this one, if I put chlorine here and chlorine here, there will be a cis. So this will be a cis metal complex geometric isomer. That's a trans metal complex geometric isomers. The last one is essentially the new category, and this is what we call the three complexes, right? Three ligand. We have a three identical ligand, so the molecular structure is just looks like that. And this is coming from your class slide, and then they said that FAC means a one faces, and an arc around the center is an MER. Is actually MER is very similar to meridirian. Meridirian means going through the pole. If you're looking at the geography classes, if you take anything like that. So MER is going through the pole, and if you imagine that this is more like a plane, right? You take one of them, and this is going through. It's almost like put a plane and put a knife and going through this. So just chopping through, okay? So this is a MER plane, MER the isomers. Whereas this one is, you can see that there is a square planar here. When you have a 3-chlorine, they form these faces, which is one of the facet of the pyramid on here. So that's for FAC-mers, okay? So just for the recap, I will do it again. So if you have the square, and then up and down, and then if you have a chlorine here, chlorine here, chlorine here, they will form the same side, and that's an FAC isomer. Okay, and if isomer, oh yeah, I got it right. I think the late night classes, I'm getting a little bit dizzy. Okay, so then what do I do is I go through the same thing. And then this time I draw that, and this time, and let me just use to represent it better. So I'm going to take the one chlorine here, and let's say I'm taking the chlorine here. So you can think about this one going through this, going through that, going through. Those are the planes, right? So when this is something that you can see that you are kind of not seeing this. So that's the plane that's going through. That is going through the MER. And if you remember the meridian, okay, this is very similar to that. So this is going through the pole, and that's a MER isomer. Okay, so those are the what you can find out from here. And then I also solved the previous exam problem, and then I start to notice something that is also called a linkage isomer, and this is something that I wanted to share it with you. Okay, so linkage isomer is coming from the understanding like this. So in the metal complex, there is always metal in the middle, and the ligand always expected to have. I wrote the L in a very funny way because L, okay, a ligand has a lone pair electrons. The other one can donating the electron to. But what if your ligand has an electron here, and let's say lone pair electron on the other side, and depending on whether this electron is connected to make a coordination to the center metal, or the other electron is making a coordination to the other side, there will be what is called in a metal, right? These two different scenario is related to the linkage. And more specifically, we have to find out which atom, what lone pair from which atom is connected to the center metal. And there are two examples I like to pick here. So here's an example of nitro, okay, and this is also NO2, but you see that the lone pair. Okay, so let me see that. The lone pair from the nitrogen is making a docking to the center ion here, right? Whereas this one is, yeah, there's a lone pair there before, But now I'm switching my position that I want to give this lone pair is docking to the cobalt in the middle. So it is the same NO2 minus ligand. Right? But like I said, there are, if you look at the NO2, I'm gonna put an NO2 here. NO2 has this oxygen, oxygen, nitrogen, and one of them has a single bond, and the other one is a double bond, and it has a lone pair electrons here. This one has a 2 lone pairs. This one has actually 3 lone pairs. That's why former charges is minus, over charge is minus, and it can have a resonance stabilization and so on, right? But now you can see that this one is an electron-rich side. They can make a bonding here, or this one is a more electric side. They can make a bonding here. So that's called a linkage isomerism, and that's what some of the previous problem was about. And which is more common? This is more common, actually, more common. And this is just the experience that the chemists find out. And you can see that this is more symmetric bonding than this is an asymmetric. Nature provides the symmetry and the balances, okay? And so this one is, so therefore its name is called nitro. And this one is sort of the cousins of nitrito is a name. Okay, so that's a linkage example of the linkage isomer. When you have this unique situation that you have more than one lone pairs that can give a site, and depending on which one is connecting here, just like here, this is an example of this lone pairs of 2 different kinds. And that's an example. Another example that I like is this compound called SCN. SCN is, you know, the CN is what it's called cyanide, right? Cyanide was, and then if there's a ligand, it's called a cyanate. And if you also have, they can also have a sulfur there. So if you draw the Lewis structure, their Lewis structure just looks like actually this. And so therefore the negative charges, the formal charge is here. Okay, but now if you can look at it, this one here, this can form the coordination with the metal, right? And this is a case of for more common, and this is what we call the cyanide, was cyanato. Okay, so this is when as a part of the ligand name, that's what it's going to be looks like. But if you look at that, wait a minute, it looks like what about this, right? So this is also possible. So I'm going to flip this away, molecule, writing this, and now emphasizing the same scenario, but there is actually small chance, but there is a chance for this lone pair forming a docking with the central metal as a ligand, right? We're talking about this, these are the ligands, but this is a linkage isomer. So in this case, the naming is also funny. It looks like an iso, cousins of thiocyanato. And that's how people can write it down. That's a little higher levels of coordination in organic chemistry in terms of the numbering. Okay, so as I promised, this section B, I'm talking about the energy split diagram, and this one is I want to actually focus on the d orbital shape itself. Okay, so let's talk about the d orbital, and this is a d orbital. And if you look at that d orbital, this is coming from your lecture slide. There are 5 d orbitals, and it's a bunch of looks like a clover leaves, except for the one in the center. This is a G to G square. Okay, so then I'm going to categorize this one into the two species. So I'm going to group these two. Okay, so why am I choosing these two as a one group? Okay, so can I move this one? Okay, I don't think I can do that. So I will just leave it make this one goes up. Okay, so if you look at that, there's an x-axis, y-axis, z-axis. You can see the Cartesian coordinate x, y, z here. And this g square are there on the axis, right? The electron cloud is focused on the populated on the axis, and this dx square minus y square, they are on axis as well, right? So these are the one on the axis. And then if you look at the other one, which is, I can circle that in a green borderline, and if you can see that they are actually in between, right? So these are the in between axis, right? So those are the one we call the dxy, dyz, dxz. Actually, this name speaks for itself. When you look at that, they are kind of go in between, or are you on top of each other, right, on the axis. And this one has a good important consequences when it comes down to understand the energy splitting here, because this is one of the class lecture, the video, the lecture slide. So when you have these d orbitals, and then let's think about, I'm going to draw this octahedral one more time. Right, there we go. So then, as you can, now I'm going to draw the x, y, z. So this time I'm going to draw, this is an x, right? And this is a y, and this is z. So x, y, z. So you guys can think about the symmetry and the octahedral, and which one is on the axis, right? And then now we are going to have this ligand. What the ligand means, each ligand is going to push the electrons to you. So let me say, okay, each side you are going to have a ligand. It's like squeezing the balloon. So there are ligands here. Every ligand is trying to, in a way, donate the electron, push the electron to the center of the one. And which one will get squeezed? If you think about it, the one that on the axis will get squeezed, and when you have an electron cloud of this, and they will get squeezed, and their energy level goes up. So which one level will go up? These two. Their orbitals will be squeezed. The electron inside of that will be squeezed out, and so the energy level goes a lot higher than those in the bottom, which is something in between. Those are the one in the bottom. So this is a case where you're seeing the octahedral energy splitting, and they are using the symbol delta. Okay, so they're putting a delta here, and then sometimes they put a delta OH because it's an octahedral based energy splitting. And this energy gap depends on whether how strong the push of the electron. If the electron push is very strong with a strong ligand, the energy splitting will be bigger. If the push is very weak, the energy split will be very small. So therefore, you can see that which one will be very strong. The famous one is actually the stronger ligand. And this is something that as a chemistry you should know. The strong electric field ligand, the most famous one is this one, the cyanide. And if you're looking at the cyanide, CN triple bond with an N. Okay. And then this one has a octahedral satisfaction. So this one just looks like that. So each one satisfies the octahedral. That's a Lewis structure, and then oxygen, the carbon here is a formal charges negatives. That's why the CN minus cyanide is a minus charges. And then that one is essentially going to docking to the center metal ion. So this carbon is really aggressive. They are negatively charged, and it almost looks like a nitrogen with a one extra electron. So that's why it looks like it. And they are the one humming for the positive charge metal complex center, and they're going to dock it, and they're going to push the electron stronger. So these are the strong electric field. The one that weak electric field ligand is something like a water. As you can see, the water has they have lone pairs, and those lone pairs electron can be used to coordinate, so they can do that, but it is a very weak ligand. So one of the problem that in the number 4 problem that I covered in the discussion problem was, what about this case, how the spin state is going to be different? And so something that you can find out is, okay, this is the Fe, water, so there's the 6 coordination, so this should have an octahedral structures of the ligand, okay? Ligand, and then this is a weak ligand, right? Whereas this one, also same thing, octahedral, but this time is a strong ligand. So you can see that the CN is a strong ligand. And then now I can see that, first let's figure out the charge situation here. So let me see. Okay, this is a 3 plus 3. This is a neutral, so therefore Fe must be 3 plus. So Fe 3 plus. What about here? Now this is a minus 3 charges, but this one from the cyanide ion minus 6. So Fe here is the same thing, Fe 3 plus. So same thing here, Fe 3 plus, Fe 3 plus. And if you look at their electron configuration, argon, if you look at the periodic table, you'll find that taking the 3 electron out, you're taking 2 electron from the 4s2 and taking 1 3d orbitals, electrons, so you ended up having d5. So that's the same case. You have 5 d orbital electrons to fill it up, but the case is different for each one of them, because when you have a weak, and I know that the higher energy is going to be dz square and dx square minus y square, because they are on the axis, on the octahedral geometries, and the one at the bottom is those xy, yz, and xz, and this is an energy split. But this energy split is pretty small compared to the cyanide. The push is really high, so this delta energy is big for the case of ion cyanide, right? And then now you're going to fill up the 5 electron, and then, if you're putting up, because energy difference is not so much, they're just going to maximize the spin state for the weak ligand, whereas this one, they put 3, and instead of putting this one up top there, they just will just take the one in the bottom, because this energy gap is so much. It's actually to put the electron in the lower energy state and trying to maximize the spin-spin coupling. So this is what it's going to have. So if you look at the spin now, the spin state is, there are 5 spins. This one has only 1 spin. So spin-wise, this has a higher spin molecule. So both are paramagnetic, but this is much more stronger paramagnetic, the one with a weaker ligand, because they maximize those. And then I can go on to a little bit. This is also I find that is interesting. And if you look at the tetrahedral, this lecture slide showing to you that if the tetrahedral, this 4 tetrahedral position is essentially in between. So therefore, when you have this lone pair electrons from the ligand, right? They are trying to make a docking. So I'm just trying to write a L. Okay, those ligands are trying to make a docking. They go in between the axis. So what do? They'll go in between the axis, dxy, dyz, or yz, and the dxy, xz, right? Yz and dxz. Those their energies will go up, whereas the relatively this one, it will go up a little bit weak, which is dg square and dx square y square. Because if you remember those, so that's why it's almost like an energy flipped. There are 3 at the top, and so this is for the delta tetrahedral. Okay, so delta tetrahedral is you have 3 higher energies and you have 2 weak energies. Compare, right? Compare that, we have 2 higher energy and 3 weak energy for delta octahedral, remember? And so this one, and it's almost like an kind of the flipped energy splitting situation for that octahedral too. Okay. There are some students saying that why can I have an optical isomer if it is not chiral? So the chiral means it's a chi means coming from the optical. There's a student that asked me about the chirality. The chiral means CHI in chiral means an optical. So this question, if it is not chiral, that's you cannot have an optical isomers. Or they actually prepare to use a word, the chiral. There is a chiral center. Chiral center. Because it has a chiral center, it can have an optical isomer. Those are the wording that most people use this way, but it means the same thing. It can have a chiral isomers, it can have an optical isomer. It is the same meaning. Okay. Would you have an Ma2B2 have 3 different isomers? Okay, so let's go back to this question the student asked. So MAB2, they can have a, so I mean I'm putting this A on the other side, right? So those are the A. So as far as I know, you can have only cis and trans isomers, and this one cannot. If you look at this, the cis isomer, they cannot put the mirror isomer. So the cis isomer of this planar square, they cannot have an optical isomer. So it will just have a cis, and there's no optical isomer pairs. So in that case, it's just 2 isomers. One is cis and the other is trans. There is no possibility for them to have an optical isomers. And for example here too, this one is they cannot have an optical isomers, whereas if you have the situation is different because this is the case for ammonia, so then they are superimposable. But this one is if this one is so replaced by ethylene diamine 2 and Cl2, then the cis this complex can have essentially 2 optical isomer pairs, right? So they are the possibility of doing this. I hope this one explained this. If you if not, leave a chat or leave a question on the Google Doc. I can answer your questions. Okay. I think that.